Hello, this is Mr. Jackson, and today in chemistry I want to talk about graphing. Okay, graphing is when you get some raw data from an experiment and you put it into a graph form. And I just want to go over some basic rules for graphing because a lot of people tend to not do it correctly. So here we go. The first thing you want to do is you want to determine a scale for your graph. Okay, so here I have some raw data, and one thing I don't want to do is I don't want to make all my lines on my graph have these exact numbers, because if I do that, then my graph will be inaccurate. So what I want to do is look at the range. So here I go from 4.5 up to 32. So anywhere, I'd like my graph to go from 0 to about 35 then, and then that would include these points. So you look at your scale. Now most graphs should be at least half a sheet of graph paper. And you want to have enough room to write on the sides of the graph with numbers, and so you can be seen and not crouch them in. Okay? And so I looked at this graph and I kind of broke it into fives. And so I decided to go by twos. I don't want to go any higher. I want to just use about half the graph paper. So if I go by twos, now the y-axis is mass. And so I'm going to go by twos as far as I can get to make sure I'm above my highest number. So this is going to be 0 down here, 2, 4, 6, 8, 10, and then 12, 14, 16, 18, 20, and then 22, 24, 26, 28, 30. Here's 32, here's 34, so it's pretty close to 35, okay? And as you notice, I didn't put a number on every line because that makes it way too busy. So you never want to label every single line. You just want to label enough lines so a person can figure out the scale. And so my scales go by 2. Okay? And then over here, I'm going from roughly 2 up to 18. So I'm going to go up from 0 to at least 20 to make sure I cover this range. Okay? Because I want to graph volume on the bottom. So I notice I have a lot more lines in the bottom, so I think I'm going to go by ones. So this would be a 0, 1, 2, 3, 4, 5, then 6, then of course 10, 15, and 20. Now, the next thing you want to make sure is you want to label all of your axes with names and units, okay? Because I want somebody to know what we're doing here. My units were grams, and my volume one was milliliters. So I want the reader to know that this is my mass graph, or axes, and so it's in grams, because you got to remember there's kilograms, there's pounds, there's all kinds of mass numbers, and I want them to know what the unit is. Over here, my volume is milliliters, and you put that in brackets either below or next to the name or the label. So now I've labeled my graph, okay? And I've made a good scale. Now my scale does not have to be the same. This scale goes by 2 and this scale goes by 1s, and that's acceptable. You don't have to have the same exact scale on both sides, okay? So after you do that, then you want to, it says right here, plot your points and draw a best fit line. Okay, a best fit line means that when you get done doing your data may not be perfect and your dots may not fall perfectly in line, but we're going to draw one based on our actual experiment. And in this experiment, we were graphing mass and volume to find the density of a material. And so that means this needs to be a straight line. But my graph may have error from my experiment, but that's okay. I can take care of that. So let's plot our dots. Here we're going to plot 4.5 on the mass axis and 2.5 on the volume. So 4.5, 2, 4, here, so 2, 4, here's 5 right there. So 4.5 is just a little bit down. And then on the mass axis, I want to go over to 2.5. So here's 1, 2, here's 2.5. And then that 4.5 would be roughly about right there. Okay, so I have to put it somewhere where it looks the best. I'm not plotting it right on a blue line. I'm doing the best I can to estimate in between. So I'm going to continue plotting the rest of these here really quick. So I have another one at 10 on the gram, and I'm going to go over to 5.8. So 5, here's 6, so 5.8 is just a little bit above, almost to 6. So that would be about right there. Okay. Then the next one is going to be 23 for the mass and 13.1 for the volume. So 22, so 23 would be right here. And then I want to go over to 13.1123, and it's just on the edge of a line of 13. Okay, so we have 22, and then 23 is in the middle, and it'd be right about here. Okay, so right about there is my best guess. Just a little bit over that line on a hair, if I can point it out. Then my last one is 32 and 18.3. 32 is going to be right here along this top line, and 18.3, here's 15, 16, 17, 18, and 0.3, a little bit above. So 32 and just a little bit above 18. So right there, almost a point there. So there we go. You can see my data looks pretty good. I got a nice straight line. I know that in density, if I have no volume of enough, I'm not measuring anything, it has no mass. So it's the legal point to start from. I'm going to draw a best fit line. It should be straight. Now, if my data doesn't always touch every point, that's okay. I just want to make sure my line's straight, and if these points all don't hit it, then it's okay, because that means there's error. And I've plotted plots before where I've had data that's a little bit lower because of an experimental error. And so I'm not trying to hit those points. I'm just trying to be close as I can. And if I'm not on all of them, that is okay. Do not try to connect every single point. And in this case, there was pretty good data. Okay? So there's my experiment. Now, what I want to do is draw a best fit line which tries to fit most of the points. So I just want to point out, if I had some other data points that were down below and above, I would still put it the best place in between them. Okay? That's a best fit line. So then it says right here, give the graph an appropriate title. Okay, so I'm going to call it a density graph, because that is what mass and volume are. So there's my density graph. So that's a pretty good graph, okay? Now, what I want to do is I want to find the slope, okay? And the slope of any line, how you do it is you don't use your data, because you see how this one's kind of missing the line? So that means there's some error in that experiment. And sometimes they're farther off. So you never use these points to do your slope. You always pick two new points. So I'm going to pick 2 points that are pretty easy to read on the graph. So let's pick a couple points. This is a good one, because see how it goes right through the squares? So that's a good reading point. And then I want to find another one, something like that. It looks like there's one right up here too. It looks like it's pretty good in this area. So let's go with this one right there. So then what you do is you go over to the side and the bottom, and you read those data points, and you find them. And the slope is the change in y over the change in x. Okay? So I got to find these 2 points and subtract them. So if I go across, this is 14, and this one right here is 28. So I'm going to go 28 minus 14, and that's the gram side of the graph. Then I go down, and then this one is 16, and this one is 8. So I go 16 minus 8, so this right here is 14 and 8. Okay, so this is my y1, x1. This is my y2, x2. So then I divide these numbers, and this is milliliters. So clear, we have 28 minus 14 is 14, and 16 minus 8 is 8. So 14 divided by 8 equals 1.75. And that would be grams per milliliter. So that's how you find the slope. You do not use your data that you plotted. You pick 2 new points off your line. You subtract the y's and subtract the x's, and then divide them, and that is how you find slope. Okay? So let's go on from there. And you're going to need to find slope on your density experiment with water. So you're going to do this with water only from your raw data on your density lab. Okay, and this will be the mass and the volume, and I want you to do that with your 3 data points. I had 4, but you're going to have 3. Okay? Okay, there's 2 more things we need to discuss. So I'm going to flip through the notes. I'm going to go beyond this next section, which we'll teach later. I'm going to go to the back of this lab where it talks about error and error calculation, as well as conclusions. what is an error? An error is something that is involved in every experiment. We were talking about that when we were doing the lab. Not every measurement we made with our instruments were perfect. We did estimations. So there's some error. And that's why all my dots didn't fall perfectly on the line. They did touch the line, but some were above and below. Yours may even be farther off. You're still going to draw a best fit straight line from the 0, 0. You do not want to bend your line in any way or shape. Okay? So how do we talk about error? Error is basically, it can be in a verbal statement about why things weren't perfect. Okay, so maybe something like, in this lab we were trying to find the density of a liquid, but we did not measure right, and the values were off, and it was hard to read the graduated cylinder, is not. This is a bad error statement. A better error statement, if you want to do it, was that we're limited by the equipment we used. We had to estimate only to 1 decimal place. We only had a graduated cylinder, and so we already measured 3 times, and those 3 measurements had error in them, and 3 times those measurements is 3 times the error. So we're limited by our equipment is an acceptable form of error. Okay, but in this one I want to do a experimental calculation one. So what we're going to do is we're going to find the average value of these numbers. So we have 1.8 plus 1.72 plus 1.75 plus 1.75 again equals divided by 4. So my average is 1.755. So I'm going to put 1.76 grams per milliliter, and that's my average. And I want you to find the average of your water measurements. Now, how do you do a percent error calculations rather than a statement? It's really simple math. I know the density of magnesium. Magnesium is in reality 1.74 grams per milliliter. And I'm pretty close to that number right here. But to find the error, you don't subtract those numbers. What you do is you find the true value, okay, and you do subtract away your experimental value, but then you divide by the true value again so that you find out how far that little bit of error was off from the whole total. And then you times it by 100 to turn it into percent. So it would look like this. It would be 1.74, because that was what I should have gotten. That's what the accepted value is, and the accepted value for water is 1.00. And then I'm going to subtract what I got in my experiment, 1.76. I'm going to divide it by 1.74, and then times it by 100. And that will tell me the percentage of error I had in my experiment. Okay, so 1.74, and I go minus 1.76 equals divided by 1.74, and I get this number, times it by 100, and I found out that I have a 1.5% error. So 1.5% error, and it is negative. And negative or positive, it doesn't make a difference. It just means that if this is my mark, then I was above it, means negative error. If I'm below it, means positive error. So the sign doesn't make a difference. We're looking at the size of the error. So that is my error calculation. You're going to do that today on your lab as well. Okay? So there, we talked about graphing, scales, labels, error calculations, and slope, finding slope. You're going to do that today on your graph. And then the last thing is writing a conclusion. How do we write a conclusion? A conclusion is a closing statement to every lab, and it only includes 3 statements. You never write, oh, I did this and did this, we weighed this, we did that. No one needs to know how you conducted your experiment. Usually that's in the procedure on the front page, which we already have. So all you want to tell the person is what you learned. And the first thing you do is you write, in this lab, we were trying to, and so in this lab, I would say, because I look at my data and what I'm trying to do, I was trying to find the density of magnesium, okay, and graph it. I was trying to find it mathematically and graphically. Okay, so that was my purpose. So I would probably finish the statement, and with my data, I would say I was trying to find the density of magnesium. And then my next sentence would be, I found, if I'm working with a partner, I'd say we found, okay, and you usually are working with partners, but not all the time. We found, I would say we found the density of magnesium to be 1.76 grams per milliliter. Okay, then I might reference and say, but that's pretty close to the 1.74, so I'm going to agree with the book, and I was actually very close. And most of my measurements were pretty close. I had some error, and that happened. Okay, and so that's what you talk about. So these are scientific statements. This is what you're trying to do, and this is what you found, and you give them a little proof from your experiment, from your data and stuff. Okay, then your last sentence is what your opinion is. So now you want to say, I or we realize, and then you want to make a statement of what you learned that day. Well, maybe you realize that the density of a material doesn't change really, even though you change the amount. So the density stays the same. So you can have a whole bunch of material. You could have, 5,000 grams, and once you divide it by the volume, you're going to still be close to this number. So it doesn't really change. Or you can talk about how slope calculations, what did you learn and what are you going to take home from the lab? So that's your own personal opinion or idea of what you learned today. So these two are scientific and then this is personal, okay? And that is all you want to write, and then you want to finish the statement. Let me show you a couple ones I've had over the years that are kind of weird, okay? In this lab, we weighed lots of samples of liquids. We then measured their volumes. We were trying to find density of these liquids. We found that if we did not weigh them right, you got bad answers. We also found the density of liquids were water, 1, and the oil was 0.88. We now realize that the density does not change the same material, and measuring volumes is really tricky. This was kind of hard because it had math and my measurements were probably bad. So some statements in here are good. Some statements are very bad. You do not want to tell people that things were hard. You do not want to say that your measurements were bad. Okay? You might want to say what you did. That's fine. This one's better. We were trying to find the density of liquids. So this other stuff is extra information we don't know. Okay? We don't care what you were doing. If you found out you got bad answers, no one wants to know about that. So you want to tell them, oh, then we found the density was this, and their oil is that. We now realize density does not change. So these would be 3 good sentences to use. So never blame yourself and never tell people that you do things wrong. That's not what you do, okay, as a scientist. You're learning to be a scientist, okay? And if you can't reach a conclusion because your lab doesn't have enough results, you can always go back and do another experiment again, okay? So that's my discussion on graphing, error statements, conclusions, and all those things that you need to be good at writing in a chemical or a chemistry lab. So go ahead, and I want you to finish the lab, do a graph for the water data, and I want you to do an error calculation for it, and then answer the questions that are in the lab, okay? Thank you very much for watching. I appreciate it.